When we simply draw a Lewis structure, we are just showing where the pairs of electrons are relative to the nuclei of the atoms that make up the molecule. But we aren't showing anything about what those electrons look like as waves. One of the things about valence bond theory, beyond correlating to the shapes of the molecules, is that it can show us where the electrons are and what those electrons look like as waves. So for instance, this second bond in this double bond has a wave pattern that looks like this red and blue lobes. So its orbital, the two electrons that make up that second bond, its orbital has a positive and a negative lobe. And those lobes are situated above and below the plane of this planar molecule. When I have a triple bond, I have two of those orbitals, one that's oriented front and back and one that's oriented top and bottom, like this one is. So those multiple bonds end up having electron waves that look something like a p orbital in a way, but it's spread over both of the atoms that are connected by that bond rather than just being a p orbital on one atom. So let's take a look at how the atomic orbitals on each of the atoms are interacting or overlapping to make those new orbitals that describe those bonds. So first of all, we'll remember that if I have a C2H4, that each of these carbons are sp2 hybridized, which means that they are both trigonal planar. And so when I think about the orbitals that these carbons are using to make bonds, I can imagine, so if this is my carbon nucleus, that I have a sp2 hybrid that's pointing out in this direction, an sp2 hybrid that's pointing out in this direction, and an sp2 hybrid that's pointing out in this direction. So those blue ones are sp2 hybrid orbitals, and there are 3 of them. And then because I've only used the s and 2 of the p's, there is a leftover p orbital that hasn't been hybridized, but is still part of that carbon atom. And so there is a p orbital that comes out of the plane and goes back into the plane of the board. So back kind of behind that sp2 hybrid. The other carbon atom has a similar configuration because it's also sp2 hybridized. So if this is my other carbon nucleus, then I have an sp2 hybrid that's here, one that's out here, and one that's out here. But my other carbon also has a p orbital that is coming out of the plane of the board and one that's going back into, it's one p orbital, but it has 2 lobes, right? One that comes out of the plane of the board and one that goes back into the plane of the board. So this overlap here is entirely between the 2 atoms. And that overlap forms what we call a sigma bond, because that overlap forms a electron orbital that is completely between the 2 atoms. So that's a sigma bond. But this leftover p orbital on each of the carbon atoms can overlap, but notice that it overlaps with a lobe that is above the plane and a lobe that is behind that sigma bond. And so if we think back to the picture that we had at first, this is this bond here that has a lobe above and below the plane of the molecule is kind of like a p orbital, and so we call that a pi bond. So that the overlap of those electrons in that leftover p orbital forms a pi bond. So remember that the Greek letter pi is the analogy to the Arabic letter P, and that the Greek letter sigma is the analogy to the Arabic letter S. So S, sigma, is sort of spherically symmetric, just like an s orbital would be. Pi, P, has two lobes, one positive and one negative, that are above and below. So the naming of these bonds, or these orbitals that contain the electrons that are making those bonds, is analogous to S and P, just using the Greek letters sigma and pi. These other sp2 hybrid orbitals that are hanging out here are the ones that are going to be used to make bonds to the hydrogen. So let's make our hydrogen yellow. So if this is my hydrogen, hydrogen just has that s orbital, it doesn't hybridize, and there's another hydrogen here with an s orbital, another hydrogen here with an s orbital, and another hydrogen here with an s orbital to make my 4 hydrogen atoms. So my hydrogen atoms are the orbitals in yellow, and notice that we get this overlap here that is completely between the 2 nuclei, and so again, those are sigma bonds. So now if we look at the triple bond, so let's look at the carbon compound that has 2 carbons and 2 hydrogens with a triple bond between the carbons. We know that these carbons are sp hybridized, so they're using sp hybrid orbitals. So if I draw my sp hybrid orbitals, my 2 carbon nuclei, and I draw my sp hybrid orbitals, remember that those are 180 degrees from each other. So my hybrids, sp hybrids, and there are 2 of those on each of the carbons. And the sp hybrids are overlapping. The sp hybrid here from this carbon and the sp hybrid here from this carbon are overlapping here to form a sigma bond. But because I have only used one of the p orbitals in that hybrid, I have 2 p orbitals left over. So I have a p orbital on this carbon that goes up and down, and I have a p orbital on this carbon that goes up and down, and then I have a p orbital on this carbon that goes in front of and behind, and I have a p orbital on this carbon that goes in front of and behind. And so just like I could overlap this leftover p orbitals on this on the 2 carbons that were double bonded, now I have 2 possible overlaps. So I can overlap here above the plane of the sigma bond and below. That's 1 pi bond. And then I can overlap here in front of and behind the sigma bond. That's my 2nd pi bond. And so I end up with 2 pi bonds, one that's up and above and below, and one that's in front of and in back of. So what we can see is that when I have multiple bonds, the first bond is always a sigma bond. So I make 1 sigma bond, and then the rest of the bonds that are between those 2 atoms are going to be pi bonds. So a sigma bond and a pi bond, a sigma bond and 2 pi bonds, a sigma bond and 2 pi bonds, right? Remember that those pi bonds have 2 lobes, just like a p orbital has 2 lobes. So it takes a red and a green to make 1 pi bond. because I have a lobe above and below, just like the p orbitals are above and below. That's one p orbital. And so in the pi orbitals, we have above and below, and that's one pi orbital, or one pi bond. Now let's take a look at why it's important to think about what those electron orbitals look like. So if I examine this molecule with the double bond, this is called an alkene. You'll learn that in organic chemistry. If I look at this double bond, remember that one of these bonds, the first bond, is a sigma bond. And so that sigma bond has an orbital that is entirely between the two carbon atoms. And if I take and rotate this side of the molecule around, I can do that because I am not going to end up actually breaking any of the electron density in between here. I can freely rotate this around, and since this is spherically symmetric, I can just rotate this around so the chlorine comes over here and the hydrogen goes in the back, and I will maintain that bond during that whole rotational motion. However, if I examine this same molecule, but now let's think about putting the pi orbital on there as well, then if I have my pi orbital, so remember that the pi orbital has this electron density above and below the plane of this molecule. Now when I try to rotate this, what's going to happen is I'm going to have to break up the overlap between the p orbitals. So remember that this overlap came from p orbitals that were aligned with each other in a parallel fashion so that their lobes overlapped. So now when I'm rotating this part of the molecule, this upper lobe of the p orbital ends up in the back of the molecule, and this bottom lobe ends up in front of the molecule, and that breaks that interaction between the overlap between those p orbitals. So those two p orbitals can't overlap anymore, and I have to break the pi bond in order to rotate this around. So if I have double bonds or triple bonds, because the same thing would apply, I have to break the pi bond in order to rotate that that molecule relative, this half of the molecule relative to this half of the molecule. So there's no free rotation around a double bond. However, if I just have a single bond here, I can easily just rotate around. So what that means is that since this rotation is not allowed because I have that pi bond, which would have to break in order to make that rotation, that means that if I have the chlorines in the back here and the hydrogens in the front, I can't simply rotate this around and put the chlorine here and the hydrogen there like I've drawn here. So this molecule is different than this molecule, where I have one hydrogen in the front and one hydrogen in the back, and a chlorine in the front and a chlorine in the back. These two molecules are different from each other, and they are called isomers. So in particular, these are called geometric isomers. And this formation of isomers is a consequence of the fact that that pi bond has the particular shape that it does and requires those p orbitals to be lined up parallel to each other, so you can't rotate about that bond. And if you can't rotate about that bond, you can't go from this to this, And so these two things are completely different molecules.